live. Hello, Kagglers. Welcome to the Kaggle reading group is what this is. Little sip of coffee, get the engines going. Today we are going to be kicking back off with the paper. Oh, no, I'm hearing myself. I've got an echo. Pause that. What was I saying? The paper that we're doing today is, as hopefully you can see from the title. We're continuing with Probing Neural Network Comprehension of Natural Language Arguments, which was a paper from, let's make sure I can see the whole chat, which is a paper from ACL, I believe, in Italy. ACL in Italy. So that happened in July. So it's a fairly recent paper. Hello, Kovis. And we started on it last week, and I genuinely, 2 weeks ago, and a lot of stuff has happened in the interim. So I don't actually remember where we kicked off. But the basic idea of this paper is that the authors are interested in figuring out if BERT specifically, but their method could be extended to other models. So they're trying to figure out if BERT specifically is, a little bit peaky, let me adjust that, actually understanding argument structure. And it's, okay, so that's a little bit of that's my spin on it. It's a little bit facetious. I don't think anyone thinks that BERT is actually explicitly modeling argument structure, right? It's not really a language model, but it is capturing information on statistical co-occurrence and sort of changes over time. Lucas says, do you speak Portuguese? That would be awesome. I do not. My second languages in order of fluency are American Sign Language, French, and then way down at the bottom, Mandarin. Way down at the bottom. And I'm not great at French. So the specific task that they were looking at is ARCT, which I think is Argument Reasoning Critical Test. What does the T stand for? Argument Reasoning Comprehension Task. There we go. It was literally right there, directly in front of me. Well, I guess behind my shoulder for you guys. And the point of the task is to be able to look at a claim and a reason and figure out between two, I believe you're supposed to determine based on the claim and the reason which of the two options is the warrant and which of the two options is the alternative. So if the claim and the reason, I'm zoom in a little bit so you can see. So if the claim and the reason are both Okay, let me see if I can dredge this up out of my reason. So the claim is the thing that you're arguing for. The reason is the evidence that you're providing. In order for the reason to map to the claim, the warrant needs to be true. If the warrant is not true, then the claim and the reason don't. You cannot use the reason to infer the claim. Okay, and I don't have my semantics textbook within reach anymore, but semantics. So basically, given the reason, since the warrant, you can get the claim. Given the reason, but since the alternative, you get the inverse of the claim. Is the idea, sorry, not the inverse, the negation of the claim. Lucas says, do you plan on reading Roberta anytime soon? Maybe. It's definitely a paper that I want to read. I'll probably put it in the next round of voting because this one I just made an executive decision because I think it's an important paper. Probably that one, and there was one that came out relatively recently by some researchers. I retweeted it, looking at learning adversarial text spans that make BERT style, GPT-2 style language models. I'm calling them language models. They're not statistical language models, but let's pretend that they do language modeling. And finding that you can learn triggers that will cause models to put out, for example, abusive language, and that these triggers will work across models. So I think that's also an interesting paper, and also people have been asking for a fishnet for a very long time, and I keep putting it in the voting, and it keeps not getting voted in, so I'll put that in. Maybe we'll finally read a convolutional paper. All right, so we read... Where did we read up to? I'm trying to remember. So we definitely talked about if you remember, please feel free to jump in the chat and be like, Rachel, section 2, or whatever it is. 2 candidate, let's see. Okay, I think we read the task description. If you're watching these videos back to back, this is probably going to be pretty frustrating for you. My apologies. It has been 2 weeks for me. Y-hat is the argmax. The baselines are a bag of vectors. Okay, we definitely read about the baselines. Did we read about the classifier? I think we did, yeah, because I remember talking about the CLS, which is the token that gives you the correct classification for the span. I forget what the CLS part stands for, but then this is sort of the label, if you will, and then you have multiple spans of tokens, and then a separating token between, here, there's none between the claim and the reason, but there is one between the warrant. We'll see. Kova says we passed the formula. Did we do this one? Yes, I remember this. Okay, so we talked about the applicability and the productivity of a queue. So applicable queues are very informative. Productive queues are, So applicable are very discriminable, are good at discriminating the two classes. Productive queues are very... Okay, so what's the difference? So applicability is the number of data points where it occurs with one label, but not the other. So a queue that's common across all words would have low applicability. A queue that only occurs with one of the labels and not the other would have very high applicability. Productivity is the proportion of applicable data points for which it predicts the correct answer. So this is like sensitivity. And then, it's kind of sensitivity. And then coverage is the proportion of applicable cases over the total number of data points. So you could have a queue that's very productive, that always tells you the right answer, but you never see it except in like 5 data points, in which case it doesn't have good coverage, so it's probably not a great queue. But very exploitable. Okay, oh yeah, I remember these particular tables. Now that we looked at... and then we stopped, I think we finished this paragraph, but I'm going to reread it real quick. And here, table 2, which I think we looked at, productivity and coverage of using the presence of not in the warrant to predict the label in ARCT. Across the whole dataset, if you pick the warrant with not, you will be right 61% of the time, which covers 64% of all data points. So, 90, I forget, there's a line from a movie, and I haven't seen the movie, and I want to say the movie is Anchorman, maybe? I don't know. If you do know, please let me know. And it is like, I don't even remember the line exactly. It was like 60% of the time it works every time, right? So in the 60% of the cases where it applies, it works very well. And Robbie says, come back. Good to see you. Good to see you. Welcome back to the stream. So, it makes sense that not would be a good queue here. I don't think we talked about this, but we have this example where the warrant has to be the negation of, so the reason the warrant, gets you the claim, implies the claim. Sorry, this special arrow I believe is implication. And the reason the alternative gets you not the claim, so if you negate, if you take the warrant and you negate it in the alternative, so instead of saying apples are good, apples are not good, that's a really easy way to get to negation. And because these are data sets that are put together by people are probably going to take the easiest possible way to do it. That doesn't necessarily mean, so if this is what people are doing generatively, right? If I'm like, hey, negate this, and you just add not, that doesn't necessarily mean that that's what people will do in producing text in a wider, array of genres and styles and instances. So something that may be very useful on a task where people generated the data specifically for the task may not be widely applicable to other things. Can I come up with another example? So the Winograd corpus, I think, is a good example. So the Winograd corpus are examples from actual text that are ambiguous. And we've talked about this a little bit. Winograd, what was it, schema challenge? Let's see if we can see some examples. So these are examples taken from text that you probably wouldn't actually say you wouldn't probably generate specifically for a task. So here is an example of a sentence. The town councilors refused to give the demonstrators a permit because they feared or advocated violence. Who feared or advocated violence? So in this case, switching the verb from feared to advocated switches the head. Bigger and then over, so it's actually center. So switching the verb will change the agent of the verb, basically, so the one that's doing the fearing or advocating. And that particular distinction in this case is fairly hard to come up with. Like if you just sort of sat down and tried to come up with a bunch of examples, it would be pretty difficult. And that's all I have to say there. Anyway, so natural language in context, in situ, if you will, in the wild, tends to be a lot more varied than the sort of things that you would come up with if you were just creating, items for a task. Good linguistic task design is really, 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 really hard. Like the majority. I don't know about the majority, but a good 30 to 40% of my PhD work was on that. Specifically, how do you make a good linguistic task? Also, not really super well rewarded in NLP. Like it's hard to get tenure if you just make lots of really cool, interesting data sets, which is kind of upsetting. Personally, it's a little bit like saying you can only luthiers or people who cut gems get to be real jewelers, and the people who mine the gems don't. Like that feels that doesn't feel good to me. Anyway, happy Labor Day. It was Monday in the US. Okay, so going back to not, and sorry, I'm weird tangent about how hard it is to design tasks well. The productivity and coverage of the strongest unigram queue we found, not, is given in Table 2, which we just looked at, or 3 minutes ago before I got sidetracked. While it is less productive in the test set, it is just one among many such queues. We found a range of other unigrams, albeit with less overall productivity, mostly being high-frequency words such as is, do, and are. So they occur a lot, but they don't necessarily discriminate well. Bigrams that occurred with not, such as will not and cannot, are also found to be highly productive. These statistics indicate the nature of the problem. In the next section, we demonstrate that our models are in fact exploiting these cues. So the point so far is that, hey, we're not modeling argument structure here. We're not doing we're not actually building formal semantic models, which again, I don't think people think that BERT is doing, but the good high performance on tasks where that is part of the task might lead you to believe that that is the case. Sip of water. Sorry, I'm trying not to drink into the mic. So let's continue our set of experiments. And I believe did we talk about the probing experiments? I don't think we did. Okay, so let's start with section 5. 15 minutes into this, and we're finally getting down to reading new stuff. Probing experiments. If a model is exploiting distributional cues over the labels, then if trained only on the warrants, it should perform relatively well. The same can be said for removing either just the claim, leaving the reason and warrant, or removing the reason, claim, and warrant. So basically, in order to do this as a semantic task and model argument structure, you do need all three. They're suggesting because the model is exploiting statistical cues, if you remove an important piece of the puzzle that would make it unsolvable for a human, it's still solvable in that it can get the right answer. But that doesn't necessarily mean that it's doing the task, if that makes sense. The latter setups allow the model to additionally consider cues in the reasons and claims, as well as cues holding over their combinations with the warrants. Each of these setups breaks the task since we no longer have an argument to match with the warrant. Right? So the correct answer should be, this is impossible, and they're saying, we'll still get an answer out. Experimental results are given in Table 3. On warrants alone, BERT achieves a maximum 71% accuracy. This leaves only 6 percentage points to account for its peak of 77%. We found a gain of 4 percentage points for reason and warrants over warrants, and a gain of 2 for claim warrant, accounting for the missing 6 points. Based on this evidence, our major finding is that the entirety of BERT's performance can be accounted for in terms of exploiting spurious statistical cues. So it would be like, I'm trying to come up with a sort of a parallel example, and it's hard. Let me take a sip of coffee. So it would be like, I got it. So it would be like in a computer vision task, if you have a training data set of people doing various professions, and the task is to label the profession. You removed the people from the pictures and you just showed the backgrounds to a computer vision model. If it was still able to guess the profession of the person in the photo, even without a person, it's not really doing the task. It's really finding informative, clusters of pixels in the background. So that doesn't mean that it's not going to be useful as a tool to help accomplish the task. It does mean that it's not doing the thing that you want it to be doing, or doing the thing that you might suppose that it is doing. Hopefully that helps. All right, Table 3. Results of probing experiments with BERT large, the bag of vectors, and BILSTM baselines. These results indicate that BERT's peak 77 performance, so we just read this. So basically, if we look at BERT on its own. Okay, so this is the full model. So this is BERT when it has access to the warrants, the reasons, and the claims, which is what you should expect. When you only have access to the warrants, you get a little drop. When you have access to the reasons and the warrants, you get a drop. And then when you have access to the claims and the warrants, you get a drop. But it's still doing, if it only has access to the reasons and the warrants, it's still doing better than bag of vectors or BILSTM. Curtis says coffee does the trick. It does. It helps. I'm also just very tired. Yeah, just a lot going on. All good things, but many good things. Which is weird. When you start removing central pieces of the problem should become unsolvable. All right. So this is sort of a data ablation experiments being like, hey, something's going on here. Something's a little bit funky. And the next part of the paper is that they're doing an adversarial test set. So the probing experiment suggests that the model is using statistical cues. Can we find what specific cues those are? And by, futzing with them, messing them up a little bit, will we get different results? So these are all evidence pointing in the same direction. All right, adversarial test set. Can I scooch this over anymore? I cannot. It's just sort of behind my head a little bit. The major problem of statistical cues over labels in ARCT can be eliminated due to the original design of the data set. Probably due to the original design of the data set. Given that R not A equals, sorry, the reason in the argument is not C. That's the, I don't have my semantics textbook with me anymore. Symbols. Conjunct, and. Given that the reason and the argument imply not C, we can produce an adversarial example by negating the claim and inverting the label for each data point. So if the claim is true, so if we say that the claim is true and we invert the label, so instead of the alternate being the correct answer, the warrant is the correct answer, we can create sort of a mirror, not a mirror image, like a negative, like a photo negative of the original data set. There we go. The adversarial examples are then combined with the original data. This eliminates the problem by mirroring the distributions of cues around both labels. The RCT authors provide a training set augmented in this way. Okay, so there already was one of these. The negation of most claims in the validation and test sets already exist elsewhere in the data set. The remaining claims were manually negated by a native English speaker. I wonder if that data set's available. We tried two experimental setups. In the first, models trained and validated on the original data were evaluated on the adversarial set. All results were worse than random due to overfitting the cues in the original training set. Okay, so models trained and validated on the original data set and then evaluated on the adversarial set. So you see the non-negated version, and then when they see, not you, the model is trained on the non-negated version. Then when it's given the negated version, it actually does worse because it's overfitting on those statistical cues, which are now pointing in the opposite direction. In the second, models were trained from scratch on the adversarial training and validation sets, then evaluated on the adversarial test set. So they were trained from scratch on all of the data sets and then evaluated on the adversarial data set. Okay. Ryan says the data set is available and it's very small. Now, that makes sense because it looks like a little bit of additional data augmentation because the original data set was already, the negated set was already offered. More coffee. Results are given in Table 4. BERT's peak performance has reduced to 53% with mean and median at 50%. So we were looking at like close to 80%, which is what human performance was, and now we are down to chance. So that is quite the drop. We conclude from these results that the adversarial dataset has successfully eliminated the cues as expected, providing a more robust evaluation of machine argument comprehension. The result better apts with our intuition about the test. Apt? Is that just a word I don't know? The result better apts with our intuition about this task. With little to no understanding about the reality underlying these arguments, good performance shouldn't be feasible. So basically, if you're not actually doing the task and actually modeling the argument structure and the semantics, then when the cues, the statistical cues that you're relying on are taken away, you can no longer do the task, right? It makes sense. So in our example of, oh God, I don't know how you do this in the example where you're trying to label the profession in a machine computer vision task, I guess. I guess the thing would be you have like a dentist, but they're in a construction site, or you have like a jockey, but they're in an office space or something like that, so that you change the cues. And if you're just tuning in to the background, then when the backgrounds are shuffled, not helpful anymore. So that way I think would be the computer vision parallel. All right, so here's some examples of the adversarial data sets. Figure 4, original and adversarial data points. The claim is negated and the warrants are swapped. So if instead of saying Google is not a harmful monopoly, you say Google is a harmful monopoly, you give the reason, instead of people can choose not to use Google, you still say people can choose not to use Google. The warrant is now all search engines do not redirect to Google, all search engines redirect to Google, and then the alternative is other search engines do not redirect to Google. Okay, so originally the claim is Google is not a harmful monopoly. The reason is people can choose not to use Google. So in order for the reason to support the claim, you need to, the correct choice would be that other search engines do not redirect to Google. So Google is not a harmful monopoly because people can choose not to use Google, and the sort of underlying understanding that you need to have there is that when you use a different search engine, you're not also actually using Google. The inverse here, the sort of mirror image or photo negative, would be Google is a harmful monopoly. The reason is people can choose not to use Google, and then the warrant is all other search engines redirect to Google. Claim is negated and the warrants are swapped. The assignment of WA and keeping this. Wait, does that make sense? Leonardo says, I didn't know Kaggle also did paper reading online. You're great, Rachel. Oh, thank you. The paper is, we were on figure 4, so I can come back down. Probing neural network comprehension of natural language arguments. So basically, do models like BERT, or they didn't do GPT-2, but presumably also GPT-2 or Elmo or other related models, actually understand argument structure? And the answer is no, which is not super surprising, but this is really nice experimental evidence of that. And I think some people who don't have a good grounding in linguistics very reasonably got excited by the high performance of models like BERT and are like, oh, NLP is solved now. We don't need task-specific anything. And I think this paper is a good, hold up now. Actually, language is very complex, and we are not doing a good job of capturing, the structure behind language using these types of models. Okay. Related work. They do this thing. This is super common in maybe chemistry papers I've seen this in, where the related work is at the end. I hate it. Medical papers, that's where I've read where the related work is at the end. The most successful previous work on ARCT, Choi and Lee 2018, Zhao et al. 2019, Nevin and Cow 2018. I wonder if that's Chris. Detour. Nope. No, sorry, I clicked too many times. We've gone down the rabbit hole. It is not Chris. Involve transfer learning from natural language inference datasets, Bauman et al. 2015, Williams et al. 2017, and utilized effective natural language inference models such as ESIM. I'm going to guess the last ones are for inference model, maybe English statistics, I don't know, man. A natural language inference model, and Infercent, Kanyu et al. 2017. More recently, Botchin et al. 2018 added FrameNet knowledge with modest performance gains. Oh, frames. It's a word I haven't heard in a while. I have another mug that's for the Berkeley Linguistic Society, and they do a lot of stuff with frames at Berkeley. I should have used that one instead. These models should be evaluated on our adversarial data set. So they're saying that, hey, just make sure you're not using statistical cues and you actually are doing argument modeling. In particular, it would be interesting if Botchin et al. Models stand out due to the inclusion of some of the required world knowledge. I haven't actually talked about what FrameNet is. So FrameNet is a manually annotated data set of relationships between entities in the world and their qualities. Example. So you can have multiple flames that have relationships between each other. So the flame apply heat would be a general category for actions where heat is applied, specifically involving a cook, some food, and a heating instrument. And then words that would, evoke, and the words that would invoke that frame would be things like bake, which is to put it in an oven, to put food in an oven and cook. Blanch, which is boiling briefly and then quenching in cold water. Boiling, which is to do in hot water that has bubbles in it. Sorry, I know these are sort of like very niche vocabulary words, and if you don't watch a lot of like cooking shows, and especially if English is your second language, these may be new to you. Broil, which is like heat from the top, like in an oven. Browning, to turn brown. Simmer, it's like a boil, but like little bubbles. Steam is steam coming up from under the food. Anyway, it's a sort of semantic grouping, and then they can have relationships to each other. And it's all built by hand by people with linguistics degrees mostly. And the suggestion here is because they are doing explicit modeling of world knowledge, presumably the model should do better. There's much recent work focusing on statistical cues in data sets in vision, so Joe and Bengio 2017, and NLP, and it's an NLP paper, so there's many more for NLP than for vision. Similar to experiments with warrants, Polyak et al. 2018 classified NLI, natural language inference, data based on the hypothesis only. A similar experiment to our probing task was performed by Niven and Cow 2018, but only with reasons and warrants. They found that independent warrant classification with shared parameters provides some regularization against warrant label cues. What? Okay, let's read that sentence again. Independent warrant classification with shared parameters provides some regularization against warrant label cues. Okay, so you would train one model on all of the warrants, sharing the parameters, and that helps you avoid relying on specific statistical cues in the label related to the specific warrant, I think. Robbie says, NLP application is less compared to computer vision. I don't know about that. Just as a for instance, as a, human who is online, I produce a lot more language data in a day than I do image data. I take a fair number of pictures. I have a pet, and I take a lot of pictures of my pet. But, on a day where I take a lot of photos, I'll take like 30 photos. On a day when I produce a lot of language, I'd produce like 3,000 words. That's a lot of language of written language, and that's not even counting the spoken language for things like this, where I'm speaking and being recorded. So, my gut instinct is that there are more NLP applications than computer vision applications, but language is harder than vision. And I'll happily take that fight to Twitter. At me. At me about that. Satyajit says, what's your name? I'm Rachel Tapman. I am a data scientist at Kaggle, and I have a background in linguistics with a focus in NLP. And then Tucker has answered what the paper is. All right. However, this does not solve the problem, since the presence of a queue is enough to increase the logits for either warrant. Okay. Yeah, we can dig into that later if it seems relevant. The original ARCT data comes with a training set created in the same way as our adversarial data set. Habernal et al. 2018a reported experiments using this training data that led to random accuracy. So this is another instance of, hey, if you try to do things with a negation of the original data set, if you are actually modeling argument structure, you should be able to handle the negation. If you're using statistical cues, all of the statistical cues that you've learned point in direction A, now point in direction B, and you should get to random chance. They suggested that it could be that high similarity between the data points made the problem too difficult for the simple models they implemented. Our work indicates the necessity of applying the transformation to the entire dataset in order to obtain a more robust evaluation by eliminating spurious statistical cues over the label. Okay. Oh, so one of the differences between that work and this work is that in that work they only used the half of the data set that was negated. In this work they used the whole data set, the original one, and the sort of photo negative where everything's inverted. All right. And then we have results. So because this is a binary classification task, 50% is a balanced binary classification task. 50% is chance. And as you can see, with the inverted data set, BERT is pretty much at chance. And unlike with the full data set where ablating the data set available to BERT, so only making the warrants, or only making the reasons in the warrants, or only making the the claims in the warrants available, doesn't seem to be helping. So that's on the full data set. You can see that just having the warrant, which should make the task impossible, BERT is still performing very well. On the inverted data set, not even having all of the data helps the performance. So Ryan says, but a picture is worth 1,000 words, vis-a-vis the is there more NLP or computer vision applications. Satish said, Ravi says, I hate text. Well, unfortunately, much data is text, so you're probably going to come across it. And Santhush says, during your research work, you use NLP with, I'm assuming, representation learning? I haven't done much representation learning. It could also be reinforcement learning. RL is a little bit ambiguous. No, also I haven't done much reinforcement learning. All right. Conclusion. ARCT provides a fortuitous opportunity to see how stark the problem of exploiting spurious statistics can be. Due to our ability to eliminate the major source of these cues, we were able to show that BERT's maximum performance fell from just 3 points below the average untrained human baseline, which was 80%, to essentially random. The untrained human here has had no formal semantics training, so presumably if you had formal semantics training, you'd be able to do a little bit better. To answer our question in the introduction, BERT has learned nothing about argument comprehension. And again, I don't think the BERT authors would claim that they are learning argument comprehension. That's not the point of the paper. That's not the point of the model. I think what they would argue is that with additional fine-tuning, BERT can perform well on argument and reasoning tasks, but that doesn't necessarily mean that the data is being processed in a human-like way, right? And the problem with that is that humans, in terms of language use and perception and production and understanding, are very flexible, right? You can understand completely novel utterances. You can I'm trying to come up with other examples, a little bit more coffee. Anyway, human language use is very complex and multi-layered, and BERT is not, right? And the same goes for GPT-2. Like text generated with GPT-2, it sort of looks, if you guys aren't familiar, we can look at that really quick. What is it? Transformer to text? Talk to transformer, sorry. So GPT-2 will generate text. Let's give it an example. Kaggle is a great place to learn about data science. All right, let's see what it says. Complete that. And so some of the ways that it's going to complete the sentence: data science and machine learning. If you learn the basics of machine learning and statistics, it's easy to understand how your data scientists work. In Kaggle, you'll work with a community of more than 50,000 fellow researchers to build your project. There's a wealth of data and ideas to work with and a community to interact with. This is a great place for any data scientist looking to get a degree or a new career to learn more about data science and machine learning. And then it has some learn more stuff. This is factually incorrect, right? For example, it's a great place for anyone looking to get a degree. Kaggle does not give degrees. If you had sort of a knowledge model of what Kaggle does, you might have like, hey, Kaggle has data sets, Kaggle has a coding environment, Kaggle has competitions. You'll notice that competitions is not mentioned here, and that's probably the most salient, the most important thing for most people. More than 50,000, I mean, technically true, but like way more than 50,000, like closer to 3 million at this point. We definitely hit 2.5 million a while back. So it's like, that's factually incorrect. If I were writing a news article and I was like, there were more than 50,000 people and there were actually 2.5 million, that would not be good reporting. So it's generating text that seems, it seems fluent, right? It sounds not unreasonable. Like if you came across this text on the web, you'd be like, okay, yeah, I can see, I think, someone who has a lot of experience with English has probably written this. There's not a lot of like grammatical errors. There's not a lot of early text generation stuff. You'd get like half words that weren't real words. So instead of like machine learning and statistics, you might get statist, and that would just be like the word that you got out, especially character level models. But the information isn't correct. The underlying world knowledge isn't there. It's sort of like someone with aphasia, right? Aphasia or language disorders, and there's a number of them. But one of the type of language disorders, you can produce, excuse me, a little sip of water. You can produce very fluent sounding speech that is meaningless. So let's see. I think it's aphasia. Let's see if I can get an example of aphasic speech. Go away. Yeah, so in Wernicke's aphasia, people will like produce connected speech. It seems fine. You can tell that they know about language, but the words they're using may not belong together or make sense. They might sort of like come up with new words that aren't real, and they don't know that they're not saying real words. If you're interested in language disorders, aphasia is really interesting to study and also just super heartbreaking. And somebody who had Wernicke's aphasia specifically and then later recovered, I'm trying to remember the quote. It was something like, when he had aphasia and he was affected by it, speech sounded like birdsong to him, right? He could tell that there was patterns. He could tell that it was, he could sort of like follow that it was happening, but there was no semantic content underneath it. And these sort of like big language models a la BERT are similar. They don't have argument comprehension. They don't have world knowledge. They're sort of producing sort of surface level, kind of like the text is being produced. It's not correct. Does that make sense? Sorry, I'm going off on a bit of a tangent. So I don't think the authors of BERT would argue that that's true, but especially people who are coming to the field for the first time and they see, the output of something like GPT-2 and they're like, oh, things are at human level. They're not. They're really not. And they're doing things in a very inhuman way, which, because as language users, our understanding and interaction with people who are with speech and text is through other humans, it becomes, I don't know, honestly a little bit dangerous if you think that you can get human level world knowledge without building it in. So anyway, that's my rant. There we go. So coming back down. Santhush says representation learning will help improve accuracy in natural language inference. Yeah, almost certainly. Pooja says, thank you for the paper. Can you please read tips for critically reading research papers? Reading along helps a lot. Oh, good. A lot of reading research papers is reading a lot of research papers. So the first couple ones you read, everything's going to be new. You won't necessarily understand what the authors did that is new and interesting, especially if it's a field you're not super familiar with. So just keep pushing through. Just keep work trucking. Thor said, why didn't they include their baselines in table 4? So these are only on the adversarial data set, and they did have the other results further up, and also they were at the page limit. So I'm guessing the at the page limit was the hashtag overly honest research methods reason. Ryan said, I don't think a human would be able to do this task without a bunch of prior knowledge. The data set is very sporadic in terms of information. So it does assume that you have some experience with like, you know what Google is, right? You know that Google is a search engine. You know that there are other search engines. But human performance for untrained people was at about 80%, assuming, I guess, some degree of shared cultural knowledge. But yeah, sporadic in terms of information. Yeah, I think it like covers a bunch of different topics. Pooja says, what does essentially random mean? So it's a binary classification task, right? So you have to pick whether, so you have two spans, and you have to pick which one correctly links the claim and the reason. And if you are guessing at random, because there's two of them, 50% of the time you'll guess A, 50% of the time you'll guess B, 50% of the time the answer will be A, 50% of the time the answer will be B. So random performance in this case would be 50%. If there were 3 classes, you would expect someone guessing randomly to be right about 33% of the time. If there were 4 classes, 25% of the time, etc. So random performance depends on the specific task, and here it is 50%. Thor says, table 3 is on the regular data set, isn't it? Performance of the baselines on the adversarial model would still be interesting. Oh, you mean the bag of vectors and the BiLSTM. Yeah. Yeah. I don't think they did that. So, good point. Yeah, I agree. That would be interesting. Masood says, hello to Germany. Ryan says, but 50K fellow researchers, not members. This might actually be true. Ryan, it's not true. You're doing that thing where humans see faces everywhere. That doesn't mean that there are trees with faces. It means that we look at some things and we interpret them as a face. It doesn't make them faces. There's a word for that. I forget what it is. Fooling yourself. Which I think, I don't know. Especially in NLP research, it's super duper easy to fall into that trap, right? Because you're like, oh, I can kind of see what someone might have been saying here with my output. Like, I sort of get to the point where a human might say this. But that doesn't mean that it's a good model that has human-like performance. Leonardo says, I know we're at the end of the reading, but what is the argument, reasoning, comprehension task? No, that's a great question. So the idea is that you have a claim and a reason. So there's a claim that you're claiming. So in this example that they're using in the paper, Google is not a harmful monopoly. And your reason is that people can choose not to use Google. So if you're a human doing this task, you have to know, oh, monopoly means I only have one choice. So in order for something not to be a monopoly, I need to have other options. And in order for me to have other options, that means that I can choose not to use Google, right? So that's sort of like the background knowledge that you have. And then the task is to pick which of 2 statements actually is background knowledge that would, given the reason, lead to the claim, and which of them is background knowledge that, given the reason, would lead to the negation of the claim, right? So if you are saying that people can choose not to use Google and since other search engines don't redirect to Google, those two things together allow you to infer that Google is not a harmful monopoly. But if you're saying people can choose not to use Google, but also all other search engines redirect to Google, then it would be true that Google was a harmful monopoly because people couldn't choose not to use it, right? So the task is to select which of the 2 provided statements is the one that correctly, combined with the reason, allows you to infer the claim. If that makes sense. So this should be the conjunct, and this should be the disjunct. The not one. Yeah, so that's the task. Roman says, what is the reason to add related work in papers? Is it necessary these days? Yes, that is the foundation of scholarship. So, I mean, scholarly papers are all conversations, and nobody comes up with something out of whole cloth. You are building on other people's work that they've done before, and you need to say what other people's work that is. Otherwise, that is plagiarism, and you will be removed from the scholarly community post-haste. Yeah, so related works are extremely important. They are necessary in any scholarly paper. If you are a student, they are necessary in your schoolwork. If you turn in schoolwork where you are using other people's work and you don't cite it, and you also don't talk about the similar things that people have done in the past, you will get, at worst a bad mark, at best a bad mark, at worst expelled. So it is extremely important to how we do research as researchers. Which, I mean, good question. If you hadn't had that background and that training, you may not know that. But yes, very, very important. I prefer to have the related works at the top of the paper because it's sort of like the temporal order, right? You see the things that were done first, and then you see the things that are being done currently by the researcher later on in time. So that's my preference. Yeah. Tucker says, do they discuss any pre-BERT state-of-the-art model performance on this task? They do. That is in the related works. Right here. So all of these models had previous state-of-the-art on this particular task. See, which you wouldn't know if you didn't do the related work, so you got to do it. Also, if you're trying to get a paper published and you include no related work, it will not get published, and you will get a scathing peer review. If you're lucky, they'll be like, hey, here's the papers you should have read, you dingus. No one would call you a dingus. They might, actually. It would be rude of them to call you a dingus. If you're unlucky, they'll just be like, I don't know who your advisor is, but talk to them instead. Yeah, people can sometimes be rude in peer reviews, which I would prefer that they not be, but. And Santhush says, in computer vision, we'll use data augmentation if we have less image data. What about NLP? How do you handle if we have less data in NLP without overfitting? So this paper is actually an example of data augmentation, and the way that they did data augmentation was that they took the claims, they negated the claims, and then they switched the labels for the warrant and the argument, which we talked about a little bit today. But basically, if this is the case, so reason and alternative, you can infer not the claim. Then if you take the negative of the alternative, you can take the positive, the negation of the claim, which is the true claim, is the idea. So that's one way to do data augmentation. Don't just shuffle the words. I see that sometimes with people coming from computer vision, and it drives. That's not how language works. If you just shuffle words randomly, it's no longer a language. Don't do that. One thing that people will sometimes do is take a text span, run it through a machine learning algorithm, and then run it back to the original language, depending on the quality of both of the directions of the machine translation. Depending on the quality of both directions of the machine translations, you may or may not get good quality data out of that, so be warned. All right. However, let's actually finish the paper. Our investigations confirmed that BERT is indeed a very strong learner. Analysis of easy-to-classify data points showed the reliance on the lower proportion of the strongest keyword than bag of vectors and BILSTM, i.e., BERT has learned when to ignore the presence of not the word and focus on different cues. This indicates an ability to exploit much more subtle joint distributional information. As our learners get stronger, controlling for spurious statistics become more important in order to have confidence in their apparent performance. Taken with a growing body of previous work, our results indicate the need for further research into the extent of this problem in NLP more generally. The adversarial dataset should be adopted as the standard for future work in ARCT. We hope that providing a more robust evaluation will help to spur more productive research on the problem. And the authors would like to thank Ivan Habernal and the reviewers for their helpful comments. So that is the paper. overall, I think it is a really helpful, is there an appendix? There's no appendix. Overall, I think it's a really helpful paper that talks about a big problem because, like I said, Sarian was sick. Oh, if you actually, reduce it to the number of researchers, maybe there are 50,000 people. I think it's really tempting to, especially if you have fluent text generation, assign human-like qualities to models. Like, that's just something we want to do as humans, right? We anthropomorphize. But that's not necessarily good. And having test sets that are adversarial and specifically help us to avoid those biases and be like, oh, hey, actually, this model is using spurious statistical cues and probably wouldn't generalize well, is a really good way to, improve our set of tools for model validation and evaluation, which is something that I've been thinking about a lot lately. Like, yeah. I mean, evaluating machine learning models is hard to begin with, but then adding in the fact that doing well on a specific task does not mean doing well on general task performance is, an additional wrinkle. So, Ron said they should have also trained on the adversarial negations and left a small non-overlapping test set and see if that went to random chance performance. Yeah. Yeah, they could have. I will say it is a short paper, so they had 4 pages. And I think for a short paper, this is a fairly strong contribution if they turn this into a long paper. Yeah, because you get to add an extra page in the for the camera ready. If they turn this into a long paper, I think that they could have definitely done more, but I was happy. Satyajit says, till now we can identify the emotions like positive, negatives, etc., but how do you handle sarcasm? Any model. Sarcasm detection is a specific task, and it is hard. Sarcasm. Yep. So there are, as you can see, quite a few papers on this, and I would start with a relatively recent paper that has a lot of citations and also has actually been published. Oh, wait, sorry, I think that was related papers. That's different versions. I'm trying to see if any of these are actually published. Yeah, okay, excellent. So this one has actually been published. Oh, yeah, I have actually read this paper. I knew that it had been published. It actually has been published in a reputable venue. So reputable venues in NLP are anything put on by the Association of Computational Linguistics. LREC, Language Resources Evaluation and whatever the C is for, which is biannual, and I don't think it's put on by ACL. Yeah, those are the major ones. I'm trying to think of other NLP venues off the top of my head, and I can't come up with any. I'm sure there are some, and I just have forgotten them. But that's my recommendation for how to find a piece of literature on something you're interested in. Thor says, oh, this is from the Clever Hans Force. Yeah, it is. Wondered why it was on my Mendeley library already. Nice read. Yeah, I think it was a good paper, and I enjoyed it. Lost Kitten says, I somehow prefer the Deca NLP approach of testing on multiple tasks when looking at how models generalize. Adversarial datasets often remind me of an arms race that nobody can win. Yeah, okay, so thinking about that. So BERT is very much like the canonical model that was done on multiple tasks. That was like the big thing about the original paper was, hey, we're doing really well on a lot of tasks with a little bit, like little Marmite layer of transfer learning. And what is the use of adversarial tasks when you could instead use multiple tasks? I think if you're trying to evaluate how well a model is doing something specific that we have good evidence for high levels of human performance in, then I think that adversarial data sets do make a lot of sense. I honestly think that we will see more adversarial data sets and tasks in NLP going forward. I know it's been very common in computer vision for a really long time. Hasn't been super common in NLP, and I think especially as we have larger models with less interpretable results that are more vulnerable to spurious statistical cues, especially like as an attack vector. That's not fun to think about, but it's definitely a thing that we should consider. I think adversarial data sets are helpful in that, yeah, it is like an arms race in that they provide sort of like a parallel to security research, honestly. Anyway. And Thor's like, yeah, sure, not that they don't have a place. Yeah. Also, multitask work, also very interesting, but I think we have a big hole in terms of the number and complexity of adversarial data sets in NLP right now. So, yeah, that's my 14 cents. I went on for a little while there. Question. Can we do simple RNN for image segmentation? I wouldn't use recurrent models for images. I would use convolutional neural networks, just because RNNs have a time bottleneck. And if you're not already having sequential data input, then it doesn't really make sense to choose to have a bottleneck you don't need. Ryan says, I think eventually the model wins in that race because with too much adversarial added in, eventually you destroy the data. Yeah. Well, I don't know, I guess sorry, I'm just thinking about the different ways that you could build a data set adversarially. It doesn't necessarily, not the whole data set has to be built adversarially. If you have like a few, a relatively small set of specific items that you are looking for and say you want to like flip the classification on, then I think that could also be an adversarial data set where the signal in the original data is still very strong, but also you have these use cases you want to avoid. Anyway, not my core research area, just something I've sort of like been keeping an eye on, been reading about, seeing what they're doing over there. And Thor says, in a sense, quite a few regular data sets try to incorporate that angle, e.g. the addition of unanswerable stuff from squad 1.1 to 2. Yeah, definitely. And the authors of this paper are not the first folks, not this paper. This paper are not the first folks to do the ablation experiments either, where removing data makes the question unanswerable. So, all right, it is 10. I have so much to do today. Let's wrap it up now. Oh, when I was like, hey, was that Chris Cow? I see that it is in fact the author. Nothing wrong with citing your earlier work. All right, so I'm going to wrap it up today. We will be back on Friday with some live coding. That's what we do on Fridays. We do live coding. If I have time this week, which I probably won't, I'd love to get some work done off screen then and show you guys what I have and then continue working, but we'll see. We're working on an unsupervised text classification and summarization problem. So, all right. I'm going to call it here. Thanks for joining me, and I will see you guys on Kaggle. I'll see you then. Bye.